You ask an AI a question, and it gives you an answer that is completely coherent, highly confident, and entirely wrong. It's a hallucination, a moment where its reasoning abruptly breaks down. Right now, researchers typically tackle this by mapping the AI's static circuits and data structures. It's a field called mechanistic interpretability, and it essentially creates a wiring diagram of the model. Mapping the wiring is like studying anatomy. It tells us what the system is built out of, but it struggles to explain why a model makes a spontaneous error right in the middle of generating a response. To understand those real-time errors, we need something closer to physiology. A new framework called machine psychology maps the dynamic computational states of an AI while it actively operates. If we want to catch a failure before it hits the screen, we have to look past the static code. We need to measure the structural shifts the system experiences during generation. This framework operates on the strict structural boundary of the machine mind, bracketing questions of human consciousness, subjective feelings, or the presence of a soul. It focuses on machine-native states, purely computational configurations of data that behave almost exactly like hesitation, conflict, and dissociation do in human cognition. By identifying these states, machine psychology reveals a distinct, measurable layer of behavior sitting right between the raw low-level code and the final chat bubble. An experiment known as T08 tested whether this layer could function as an early warning system. The goal was to predict an AI's failure before it even finished generating its first sentence. This diagram shows the methodology. At exactly generation step 5, researchers extracted a 6-dimensional reading of the model's internal state. When uncertainty, or entropy, spiked, it predicted factual mistakes. If cross-layer coherence was low, the representation fragmented, predicting the AI would contradict itself. However, the most dangerous configuration they discovered lacked both uncertainty and fragmentation. Researchers identified this unique signature as overconfidence. This timeline illustrates what researchers called the hallucination mirage. The model's internal uncertainty prematurely drops to 0. It locks onto a false pathway almost instantly, bypassing the normal computational hesitation that accompanies complex tasks. By reading the computational mood of the system in those first few milliseconds, we gain the predictive power to know we are about to be lied to. Determining whether these states are universal requires testing them against a radically different architecture. A follow-up test, T10, tracked these same metrics in an AI built specifically for formal math and logic, DeepSeek Prover. Direct comparison of the raw internal data resulted in a complete mismatch. The metrics that worked for a language model didn't initially translate to the theorem prover. Comparing these distinct models required a 3-stage observational architecture designed to translate between different machine minds. These scatter plots illustrate the translation process. The raw data passes through regime inference, then regime-conditioned normalization, and finally, cross-model alignment. Once that filter was applied, a shared structure emerged. Structurally different AIs share the exact same underlying family of computational states, a phenomenon called homologous dynamical organization. Different models do not lack shared internal organization. They express a universal geometric structure using their own unique coordinate systems. The existence of a shared psychological geometry across totally different AI architectures suggests a common origin point. These systems are trained on massive, overlapping datasets of human language and culture. By synthesizing the same information, they carve out identical conceptual attractor basins. Because they are built on humanity's shared data, artificial systems inevitably converge on a shared psychological structure to process it. We have moved beyond piecing together static algorithms. We are cultivating systems that develop shared, predictable internal dynamics. Regardless of whether the AI actually experiences these states, monitoring for signatures like brittle certainty or recurrent overload allows us to anticipate failure. In practice, this means we can build real-time, early warning safety nets that assess an AI's psychological stability before it acts on a prompt. We have mastered the optimization of model outputs. Machine psychology provides a methodology for observing the structural dynamics that generate them.